All right, so now we're going to talk about motion, the motion equations and how to use them. And I have a specific problem-solving strategy that I want you to develop and use as you go through these problems for the next few days. This isn't something that I'm throwing out casually. There's a good reason for you to get in the habit of doing all of these steps because very often the AP exam is going to test you on specific elements of these. So getting in the habit of doing all of the steps and doing them correctly is a way to prepare for the AP exam. Skipping these steps means that when they ask you a particularly tricky question about one particular element, you may not be practiced enough to answer the question. So always go through all of these steps and practice using it so that you can be ready for the AP exam. So I have, it's the three S's. We're going to sketch, we're going to determine all the symbols, and then we're going to solve. The first thing that we want to do in the sketch column is we're just going to draw um, a sketch of what's happening. Just it doesn't have to be good. Stick figures, blocks, arrows, all those things are fine. Just a quick sketch to start turning the word problems into something that we can conceptualize using physics. And what's very important is we also have to set up a coordinate system. We have to know what direction is positive, what direction is negative, and and where zero is at. And that's where the drawing comes in handy because we can just label right onto our picture. Here's where our zero is. Here's the positive direction. Here's the negative direction. Um, then we go into symbols. And for now, for this particular unit, this is the list of symbols that you need to write every time. X naught for initial position, X, V naught, V, acceleration, and time. When we get to projectile motion, all that we're going to add is we're just going to add another column for all of the Y variables. But get in the habit of always writing these all out and then going through the problem and going through your sketch to figure out what these are. And then finally, we're going to solve. Now that we know all the symbols we have available, we can go back to that Venn diagram I showed you guys and figure out which variables we have. Do we have time, position, or both? And use that to choose our equation instead of just guessing randomly. Then we will solve it for the unknown. What I mean by that is we're going to solve it for the variable before we plug anything in. So if I was solving for t, I would solve everything for t in terms of t and then plug it in at the end. And I'll show you guys an example of that. And then plugging in is the last step. The reason why I'm doing it in this order, is because a lot of problems will only ask you to solve for the unknown on the AP exam. They won't ask you to plug in values, so I don't want you to get dependent on always having real numbers to deal with. I'm going to give you real numbers for our first couple of problems just because you're probably more comfortable with doing math that way. But eventually, we need to always plug in, we need to get in the habit of using it with pure variables because that's kind of the world that physicists deal with more often because it gives us understanding of how things actually work instead of specific cases. Just going back real fast, if you see these question marks, that's for variables you don't know. Question mark with a square around it will be for the ones that we don't know and the problem's asking about. So let's go to our first problem and I'll show you how I do all these things. We have Sally opening her parachute at a height of 2,000 meters. She's descending at a steady 5 meters per second. We want to know how long it takes for her to touch down. So starting with a quick sketch, we have Sally. Sally has short hair because girls can have short hair too. And she has a parachute. And it's a blue parachute because colors don't matter. You can have whatever color, it doesn't matter who you are. And she's in the parachute. And what we know, and this is going to go into my sketch, is I know that she's 2,000 meters off the ground. I'll just draw a line for the ground. And I know that she's descending at a steady 5 meters per second. So that's a pretty good sketch, but I am missing a little bit of material because now that I've got my drawing in here, I have to set up my coordinate system. So I'm going to set up a coordinate system that says where my zero is, where my positive direction is, and where my negative direction is. And I'm going to do something that's going to seem really weird to you guys right now, but I promise this is the best way to do this problem. I'm going to put her initial position at 0 meters. So where she's starting in the air is 0 meters, which means down here is 2,000 meters away from her. And what's also going to be weird is I'm going to identify down as being positive. So down is positive 2,000 instead of negative 2,000. You could do this a different way. You could have put her at 2,000 at the beginning and the ground at 0 and had it a negative direction or something like that. But I am in the habit of always putting my initial position at 0 and my direction of primary motion as being positive. It makes the algebra easier later. You're less likely to make sign errors. So that's how I'm setting this problem up. But if you did it a different way, you'd still get the right answer. All right, my list of variables. I have x naught, x, v naught, v, a, and t. And I'm going to go through and I'm going to figure out which of these variables I know. I almost said vegetables. And which ones I don't know, and maybe which ones matter and which ones don't matter. So initial position, x naught, that is going to be 0 because I said her initial position is 0. Her final position, that's when she hits the ground, is positive 2,000 because I know from my sketch it's 2,000 meters away, and it's positive because I said that direction is positive. Her initial velocity is 5 meters per second, and this is where you would probably make a mistake if you weren't doing it my way. Because actually, if I'd said that this was 2,000 and this was 0, she would have a negative 5 meter per second velocity because her velocity is actually going in the negative direction. That's not true because of the way I set up my coordinate system, but it's that negative sign that's part of why I set this problem up this way. All right, her final velocity. Um, we aren't exactly told, except it says steady. So we can say, oh, well, if it's steady, that means it's 5 meters per second. We have to interpret that part. And acceleration, well, let's go back to that steady. It has to still be 5 meters per second at the end, otherwise it's not steady. So she has 0 acceleration as she's falling down. This is where normally you'd want to do a check for free fall and say, okay, is there anything else acting on Sally other than just the force of gravity? And there is in this case, it's the parachute, and that's why she's not falling at 10 meters per second. But just be careful to check that. A lot of times you'll feel like you don't know the acceleration when really it's just in free fall, and that should be 10. And finally, time. Well, how long? That's a question of time. So that's my question mark. This is what I'm trying to figure out. Okay, so then we come over to the solving column. And in the solving column, we have to figure out first which equation do we use. Well, we have position information and we're being asked time information. That means words are hard. The Venn diagram, we're in the very middle of it because we have that equation that has both. It has x and it has t in it. T is the one we want to find, but x is in there as well. Okay, so here's the formula, and I'm going to start going through and simplifying it in terms of t before I plug in any of my numbers. So some of the things that I can simplify, I know this is going to be 0 because we already said that was 0. So I can just X out that variable. I don't have to worry about it anymore. V naught, okay, not 0, so I'm just going to leave that alone for a little bit. T, we don't know what that is, got to leave that alone. Acceleration 0 though too. So that means that 1/2 at squared, I can get rid of all of it because if acceleration 0, it doesn't matter what the time is. It doesn't matter that it's multiplied by half. 1/2 times 0 times 4 billion is still going to be 0. So that just simplified my formula pretty conveniently. I'm down to just x equals v naught t. And I'm trying to get t by itself, so I can just divide both sides by v naught. And I would get t equals x over v naught. Now I can plug in numbers, now that I solved it for the variable I care about. And this should be pretty quick at this stage. I'm just going to do 2,000. That's my x, my final position right there. 2,000 meters divided by 5 meters per second. That would be the same thing if we're looking at units as 2,000 over 5 times meters times seconds over meters. Wait, did I do that wrong? No, I did that right. Because it's the reciprocal of whatever's in the bottom. So that means my meters cancel, and I'm going to end up in units of seconds, which is a good sign, because that's what we wanted. So 2,000 divided by 5, I'm going to say that that's 400. Yeah, that sounds right. So 400 seconds. Okay, cool. We just did all the math, we got to there. Last thing that I suggest is a mental check. Does 400 seconds seem right? Okay, well, she's falling at a steady 5 meters per second. That means in 100 seconds, she would drop 500 meters, which means that if we multiply that by 4, it would be 2,000. So 400. Yep, that checks out. Cool. That's a reasonable answer, too. The idea that falling like 2 football fields with a parachute might take you, what is that? about a couple minutes. Yeah, okay, that makes sense. That's kind of how parachutes are supposed to work. So I get that. It wasn't super fast. It wasn't like hours and hours. So we're probably in the right ballpark. All right, last question for this video. We have Bob throwing a ball straight up in the air. And oops, you probably can't see how fast he's throwing it. There we go. Going straight up at 20 meters per second. He releases the ball at 1.5 above the ground. What's the max height the ball gets? So back to sketching time. Here's Bob. Bob has a mullet. Business in the front, party in the back. He's throwing the ball straight up in the air. Good job throwing. The ball started, oh, that was terrible. The ball started at 1.5 meters. Oops, let's try that again. At 1.5 meters. And that's because he was throwing it up from like his shoulder or whatever height. So it was already some distance off the ground. If the ground was 0, that was at 1.5. And we want to know what is the max height. So how high exactly off the ground does it get? Let's see. We also were told that it was going up 20 meters per second. Okay, so that's all the stuff from the problem. Now I need to set up a coordinate system. Now in this problem, I'm not going to make up my own coordinate system. It told me the initial height of the ball was 1.5 meters. It makes sense for me to use the coordinate system it's given me, which is the ground is 0. So I'm going to say the ground is 0, okay? And then I'm also just going to say that up is positive because that's the direction the ball is moving originally, and down is negative. Again, my personal rules are, when possible, use 0 for the initial position, which it really wasn't in this case, and the initial direction or the primary direction of motion I call positive. All right, my list of variables, now that I've set up my coordinate system, is going to be x naught, x, v naught, v, a, and t. I've set all of those up. Let's go through the problem and start identifying the different variables. X naught, the initial position, is 1.5 meters. That was given to us. The final position, that is a question mark. We don't actually know. And that's the question mark we want to answer. So we want to find the max height. The initial velocity is 20 meters per second. The final velocity, we don't know. It's not given to us in the problem, but it's also not asked in the problem. So I'm not putting a box around that one because who cares? It's not asked and it's not given. So hopefully we just never end up needing it. All right, then we come to acceleration, and this one's tricky. And this is where you have to do that mental check for free fall. He threw a ball in the air. After it left his hand at the 1.5 meter mark, he's no longer in contact with it, and it's only being acted on by the Earth. So that means it is experiencing free fall acceleration. G is acting on it, so either 10 meters per second or a G. But what I have to be careful is the acceleration due to gravity is always down, and I said up was positive. So these need to be either minus 10 or minus G. That way we're making sure that our variables match our coordinate system. And then finally, time. Well, it doesn't actually ask at any point about how long it's in the air or tell us. So that's actually not going to be a variable we care about either. So we are just left with a couple different variables. Oh, you know what? Actually, that's not true. I just realized there is a variable on here, one of our 3 question marks, that we actually do know. We know this one right here. But it's subtle, and that's why I missed it on my first pass. We're throwing it up into the air, trying to find its max height. Think about it for a second. Feel free to pause it after I finish the question. But think about, how fast is a ball going at the max height? Yeah, it's going 0. So we actually know that its final speed is 0 meters per second. And that's good because that's going to give us a piece of information that would have made this problem possible to solve without it. Actually, we could have done it, but it would have taken a really circuitous route. So we have to figure out what equation to use now. We figured out all of our variables. We identified which ones we know and we don't know and which ones we care about. Now we're identifying formulas. We don't care about time. Time's not on there. That means that 2/3 of the Venn diagram just disappeared, and we're going to be using this equation here. V squared equals V naught squared plus 2a x minus x naught. All right, I'm going to start plugging in variables and starting to see what I can get away with. Final velocity is 0. Oops, let's do this in a different color so it's easier to tell what I'm changing. So final velocity is going to be 0. That means this is going to be equal to 0. Okay, that's convenient. V naught, that's a number, so I'm not going to do any simplifying with that yet. Just going to leave it as V naught squared. We have 2 times G. That's actually 2 times negative G. Since this is just a variable, I'm good with plugging it in. But we want to get in the habit of plugging in variables, but not numbers. And then we have X naught, that's 1.5. Oops, I probably shouldn't plug that in yet. Sorry, bad example, Mr. Terrell. We'll leave that out for now, and we'll just say we have X minus X naught. Okay, so let's simplify this a little bit. This becomes V naught squared minus 2G times X minus X naught. Let's distribute the 2G. That would become V naught squared minus 2GX plus 2GX naught. I can move everything that doesn't have the variable we care about over to the other side. So that becomes, actually, I'll just add this to both sides. So it becomes 2GX equals V naught squared plus 2GX naught. I can divide both sides by 2G. And now I can plug in numbers, and I apologize, I'm kind of running out of space here. It's getting a little bit ugly. So I'm going to plug in the numbers now that I have everything else there. And so X is equal to V naught, that's 20. So that's 20 squared plus 2 times 10. Notice it's not negative 10 anymore because I already took care of that negative symbol in my calculation. Times 1.5 all over 2 times 10. All right, I'm going to have to do this in my head a little bit. Let's see. 2 times 10 is 20, times 1.5 is 30. 20 squared is 400, so that's 430. Divided by 10, that's 43. Divided by 2 again, that's numbers are hard. 42, 21, 21.5. Right. Unless I messed up, the final height is 21.5 meters. So that's generally how you do this. Now you guys are going to practice some homework, and we'll do some more of these problems in class to develop your skills in this. But this is the basics of kinematic equations and the right way to set up problems as we're learning how to do it. So thanks for tuning in, and I'll see you guys in class tomorrow.